Hello, everyone, and welcome back to the exciting world of CSE and Stat 416. Today, we are starting our last unit of the quarter talking about this thing called deep learning, which is something that you may or may not have heard of in the news or on articles about ML systems that perform to near human performance in a lot of complicated tasks. So today, we're going to try to piece apart what is this deep learning thing trying to do and trying to understand why they're so successful. In this video, what I'll start us off with is kind of the mechanics of how the model is built up in sense of what it's trying to do, how it actually makes predictions. In class today, we're going to focus a lot more on a bunch of hyperparameter choices you can make, particularly things about how you organize these networks or what types of these things called activation functions you use, and how you actually learn what the right neural network is from data directly. So in this video, we're really going to be focusing on a bunch of small examples done by hand to make sure we understand the intuition of what these things are trying to do. And in class for today, we'll actually talk about how do we learn these things from data. So the field of deep learning is really focused in this kind of pseudo approximation of how human brains work. They're trying to come up with a model that behaves somewhat like a human brain, and very, very loose approximation. I'll explain in a little bit. But these kind of types of models have generated a lot of buzz in the world when thinking about machine learning, that they end up being very, very successful in a lot of particular tasks. And in particular, we'll talk a little bit about how these neural networks or artificial brains, usually there's a big component of them that's their structure. And so the term deep learning comes from having these networks that are connected in very, very deep layers. And they can learn very, very complex functions. So in this video, we'll talk about neural networks, what the model is, kind of how they work. There are a lot of methods and techniques and tricks people do in deep learning to make these things work in practice, and we just aren't able to cover every single one. We want to make sure we have a solid foundation in what these models are doing so we can go tackle them in our own applications after this class. Now, what I mean by these models trying to loosely approximate your brain, what I mean is that a neural network is composed of a bunch of what we call artificial neurons, or just neurons for short. They're all these individual circles in this diagram. And each neuron is connected to other neurons with edges. And the big idea of how neural networks work is somewhat like how our brain works. Neurons decide to fire based on how much input they're receiving from other neurons. So you might have these neurons, all of these ones in this column, kind of firing signals to this one neuron. And again, they're usually these really densely connected networks. So each one is like referencing others, many others, and those others might be referencing others. And each individual neuron here makes a determination based off the inputs it's receiving, whether or not it should fire or what it should fire. And this is kind of like how a brain neuron works, where you get kind of electrochemical signals coming in from the dendrites in your neuron. Your neuron has this kind of threshold for which it has an activation firing. It fires, and then that signal goes on to other neurons. And in some sense, it's an almost magic that this network of really, really simple units that take in inputs and make a decision if they should fire or not, can form the most complex human behavior we can think of. Because at a very high level, that is what your brain is doing. All the neurons are choosing to fire based on signals they're receiving from other neurons. And all of that giant orchestration kind of gives us all of human thought and behavior. And we're trying to, in some sense, approximate that in a very, very loose fashion in an artificial manner. So we'll generally organize these neurons into layers. So we'll have a layer here, a layer here, a layer here, a layer here. This is different than generally how your brain works. Your brain has very dense connections from all not every neuron to every neuron, but lots of neurons crossing to each other. We're going to simplify things a lot. We're going to put the neurons in layers and have connections go from one layer to the next, and then that layer to the next, and then that layer to the next. So it's kind of this like feed forward behavior. It's not this complete connected system. It's kind of structured in layers. And we'll talk a little bit more about what these layers represent, what they mean. So I want to zoom in for a second to think about one particular neuron. And in order to understand that, we need to think back to our linear classifier. And I'll show you that each individual neuron is doing something like linear regression or linear classification. In this context, I'm going to focus on classification, but all of the things we'll talk about today for neural networks apply to regression as well. So imagine trying to make a linear classifier. Remember, we said we had a bunch of examples that might be positive, a bunch of examples that might be negative, and our job was to learn a line, an equation, score equals W0 plus W1x1 plus W2x2 plus WDxD, that kind of goes through and separates these points in a very clean manner. Now remember that in order to learn this type of classifier, you had to assume some type of model. So in general, in the old days, what we did was we did something like use logistic regression, do maximum likelihood estimation to find the line that separates the data the best. But here we're going to use a linear classifier as sort of a building block in a much more complex model. I'll kind of explain what that's doing. We're going to make a couple twists on this idea of a linear model, but we're going to essentially be doing some kind of many separate kind of linear classifications, learning coefficients that then make us make predictions. If the score was positive, we'd predict positive. If the score is negative, we'd predict negative. So each individual neuron is going to act like one of these individual linear classifiers. So each neuron is going to be represented by kind of two components. It's going to be represented by two components. One component is going to be this kind of linear classifier component, this kind of blue circle right here. What it's going to do is we're going to compute some score based on a bunch of coefficients we learned. So we're going to learn a bunch of coefficients, W0, W1, W2, all the way to our D dimensions. We're going to represent each input as its own kind of what we'll call an input neuron. In some sense, these are kind of dummy neurons. They don't really do anything except just give an output that's the same as the input that they received. So then those outputs become inputs to our neuron. And that neuron is going to do a kind of weighted sum in a very similar manner to how we computed scores for linear classification. So we're going to say that the score of example X will be this weighted sum. So we're going to have to learn what all these W coefficients are. We'll talk about how to learn that later in the lecture. But we're just going to make do this weighted sum, and it's going to give us a number. Now, if we're just doing kind of plain old classification, you might say if it's positive, if the score is positive, then predict positive. If the score is negative, predict negative. But what we'll do is something slightly different, and this is why I'm showing a kind of more complex picture, is that we first compute the score using this kind of weighted sum of the inputs, and then what a neural network will, or a single neuron in a network will do, is it's also equipped with what we call an activation function. An activation function says, for this particular score that we just computed, what should we output? And in this video, I'm going to focus on one type of activation function. We'll see in class today that there are lots of different types of activation functions. But the one that we'll talk about that's the most straightforward is just the sign activation function, which is if the score is positive, predict positive, or the label 1. Otherwise, if the score is negative, predict the label 0, assuming that we're trying to predict between 1 and 0s. So very, very similar to our just plain old classification setup. Using a linear classifier. We learn weights, we do the weighted average or the weighted sum, and then we pass that to a thing that takes that score and comes up with an output. And the simplest thing to do would be the sign function. So here I'm showing you sign of score of X. So this bit right here represents the score, and this bit right here represents the activation function. And again, there's different ways that you might specify an activation function. So this, again, is just talking about a single neuron. A single artificial neuron, which we sometimes also call in the other machine learning literature, calls this a perceptron. I'll use the term perceptron and neuron interchangeably. Technically, people have a fancy definition for perceptrons. We won't focus too much about that. But this is just one unit that we'll use as a building block. So this one unit has a bunch of incoming connections. It's inputs. And we weight all the inputs by the corresponding coefficients we learned. We add them all up, pass them to our activation function, and it says output either 1 or 0, in this case of just the sign activation function. It turns out that this very simple one unit neuron can actually learn some types of functions, that we can actually represent some types of relationships between inputs and outputs using just this very simple, and maybe it doesn't look so simple, but it doesn't have too many other things going on, type of model. So it turns out that we're able to learn Boolean functions with these simple neurons that don't have a lot of other connections. It's just they have inputs and they have an output. What I mean by Boolean functions, they're things that you should be familiar with from a programming context. Things like and, or not. You can learn any relationship between inputs x's and y's if it's a Boolean function with some kind of constraints. I'll talk about that in a second. You'll be able to learn the y's that relate to that. So let me give you a concrete example. Suppose you want to represent the relationship x1 or x2, where x1 and x2 are your inputs. So say you want to represent the relationship x1 or x2. Sometimes when we think about Boolean formulas, we think about truth tables. So for all combinations of x1 and x2, either being 0 or 1, what should the output be? So if x1 and x2 are both 0, usually we mean 0 is false. Then the y should be 0, because false or false is false. If we consider the second row, where x1 is 0 false and x2 is 1 true, false or true is true, so the output should be 1. Similarly, if we had true or false, the output should be true, and if we had true or true, the output should be true. So our job is to take this neuron. This thing right here is going to do our score, and it's going to do our activation function. I'm just going to call that AF. So we need to pick a W0, a W1, and a W2. No, I usually will use a what we might call a dummy input or a separate neuron to represent a constant input so that we can have a coefficient for the intercept. So we'll have a W0, a W1, and a W2. And my job is to figure out what should W0, W1, and W2 be, such that for all of these settings of x1, x2, we get the proper y output. So I'll show you how to do OR, and I'm going to give you some time to think about AND. So here's what I claim. If you use W1 equals 1, and W2 equals 1, and W0 equals negative 0.5, you will be able to learn, or you will have learned, this OR relationship. Because remember, what we're doing is we're taking W0 times 1, because there's no x0, plus W1 times x1, plus W2 times x2, and then we're feeding that into the sign function, or activation function. Oops, sign of score. So let's just consider, I don't know, this row. 0, 0, and the output should be 0. So if x1 and x2 are 0, then we'll have W0, which is negative 0.5, plus 1 times 0, plus 1 times 0, which is equal to negative 0.5. And if we take this kind of sign function, and sign being is slightly defined differently so that when it's negative, it outputs 0, that will then output 0. So we output negative here. Same thing if x1 and x2 is 0 and 1. We plug this in, we'll have a minus 0.5 plus a 1. That gives us a positive 0.5, which then when we sign, takes us to 1. So this gets a plus. Same thing if we had the x1 being 1 and x2 being 0, we get a plus. And then if both of them were 1, we'd get 1 plus 1 minus 0.5, which is 1.5, which then also gets rounded up to 1 when we take the sign of it. So again, I just came up with these weights by hand. In general, we're going to have input data, and we want to learn what are the right weights to get the right outputs. But I want to just give you a second. I want you to pause the video. I want you to try out, can you come up with weights for W0, W1, and W2 such that we can learn the AND Boolean function, where AND is, it should output 1 only if both x1 and y2, or sorry, x1 and x2 are 1. Otherwise, it should always output 0. Pause the video, try this by yourself for a second, and then we'll talk about it. Okay, so now that you've had some time to think, let's think about how we can come up with these coefficients such that this relationship of W0 plus W1x1 plus W2x2, and then when we take the sign of that, gives us values that match this table. So the kind of intuition is we only want this thing to be positive or output a number greater than 0 if both x1 and x2 are positive. So what I might think is, since x1 and x2 are equally relevant in this problem of x1 and x2, I'll just make both of these 1. So when both of them are on, we'll have 1 plus 1, which is 2. And if only one of them was on, then we'd have a value of 1 from the sum. And if neither of them are on, the value would be 0. And then I just need to pick a coefficient or an intercept that sets this off the right way, such that only if one of them was on, meaning the value from their sum would be 1, it would be negative overall. And so one such number you could choose is negative 1.5. It turns out there are a lot of different weightings you could do here. You could double all the numbers, that should be fine. You could also slightly tweak them, move one up a bit, one down a bit. So there's not usually going to be a unique solution for something like this, but you can go about reasoning about how it can make predictions with these coefficients. And you can imagine that, even though I haven't told you an algorithm, how our goal is to try to learn these coefficients from the data directly. That's a neuron, one building block that we'll use in our neural network. Now, the reason I describe neural networks as being these huge connections of neurons is because these neurons on their own are rather limited. They can learn things like and or, but they can't learn all possible Boolean functions. It turns out, one I mentioned before, one of the very common counterexamples for types problems that models usually can't solve if they're too simple is the XOR problem. XOR being a Boolean function that's true if only one of the inputs is true and false otherwise. So we have if x1 is 0 and x2 is 1, or if x1 is 1 and x2 is 0, then it outputs true, otherwise it outputs false. It turns out there is no way to get this perceptron, or single artificial neuron, to learn the right coefficients to perfectly predict XOR, even in a very simple kind of truth table with only 4 possible inputs combinations you can have. And the reason is perceptrons, or artificial neurons, are trying to learn linear classifiers, right? I mentioned that the kind of backbone for this was a linear classifier, and then we just stick it through a score function. That score function then goes into an activation function, which is a plus 1 or 0, depending on if it was positive or negative. So because if your data is not linear separable, one artificial neuron won't be able to learn that thing. So the trick that people do is they change this model to combine many neurons together. The idea is combine individual perceptrons to build a neural network that can learn more complex functions together. So our idea was we'll still have our D feature inputs and our intercept. And then one neuron will try to learn as best as it can weighted coefficients such that when passed to the activation function, gets an output that's close. So this will be one neuron. It takes the score from the inputs, and it takes the activation function. And we'll have many of these neurons that then we use as inputs to yet another neuron. So I'm now putting them in a layer where I have my purple dots showing the inputs, the things that just represent the raw data. Then I'm going to make a series of neurons that learn from that data some coefficients, and then take the outputs of those neurons and make them the inputs to another neuron. And this other neuron is going to have to learn its own set of coefficients to take the outputs from these things and move them here. So we're going to have to learn a W0, W1, W2, and WD. We're also going to have to learn another W0, W1, W2, WD. And then we'll learn once those now go fed into the neuron, they get outputs. We use those outputs as inputs for the next neuron. So we're going to have to learn yet another set of W0, W1, W2, WD. Note, all of these coefficients will probably be different from each other. Even though I'm using the name W0 and so on for all of them, they probably are learning different coefficients at each step, so I can learn a more complex behavior. We call this segment here a hidden layer. A hidden layer. The reason is that this side on the far left is what we call the input. This side on the far right is what we call the output. And everything in between is kind of intermediary steps to compute the output, potentially with more neurons that are fed into others. And so we call these hidden layer or hidden layers. You'll imagine that we can actually have more than one. If you want to put many of these in sequence, you totally could. And what we're really doing is just saying, okay, well, each neuron acts as its own. So it's going to compute the sign of W0. And I'm going to specifically be talking about the Dth neuron. So maybe we'll say like the output from neuron D will be the coefficient W0 for the Dth neuron plus the sum over all i's from 1 D of Wi for the Dth neuron, and then x of I. That gives us a number, a score that we can output, and then we use that score as input for the next thing. And in general, these more complicated networks that you link things together, again, we have our input, we have our output, and we have our hidden layer. If you stack these up in the right format, in the right structure, you can learn more complicated functions like XOR. The intuition is that without even thinking about neural networks, you can represent XOR as a more complicated Boolean formula. XOR, another way of describing it, is x1 and not x2, or not x1 and x2. So that's a more complicated way of saying what XOR is. It's x1 and not x2, or it's not x1 and x2. So what we're going to do is we're just going to put each of these clauses, since we can learn, actually I'm going to use a slightly different color here. Since this clause on its own, x1 and not x2, is something we can learn with one individual neuron, we'll try to make a neuron that learns that one thing. But we'll make another neuron, maybe call it V2, that learns this other part of the formula. Not x1 and x2. And then overall, we'll combine both of those two things to get us the overall result, because these are just two ORs. It's V1 or V2. So when you can represent simple formulas like just an and or just an or, you can learn one neuron to do that. And so what we're really doing here, and I've set up all the coefficients, these coefficients work together to make the proper XOR output. So when x1 is 1 and x2 is 0, it will output 1. Now, there's a lot of kind of steps in here, but I think it will help to just do one example. So let's consider the case where x1 is 1 and x2 is 0. Now, if this is the case, the output should be 1, right? Because only one of them is true. So in order to compute this, in order to compute what the output is, we had to figure out what the outputs for these hidden layers are. We need to figure out this output and this output. So we'll start with V1. I'm going to say V1. Well, what's the output of V1? It's going to be minus 0.5. That's its intercept term. plus 1 times x1, in this case that's 1, minus 1 times x2, which is 0, minus because the coefficient there is minus 1. This will just be equal to negative 0.5 plus 1 minus 0. That's going to be positive 0.5. When we feed this into our activation function, our AF, this will output 1. So the output for this little neuron right here is the number 1. What if we consider the second neuron in our hidden layer? So I use green for this one. V2. Well, its input coefficient is minus 0.5. Then minus 0.5, minus 1 times 1 for feature 1. The coefficient for feature 1 is minus 1. And then the coefficient for feature 2 is plus 1. So plus 1 times 0. This gives us negative 1.5, which fed into our activation function will give us 0. And now we just repeat the process. Now that we have our outputs for those 2 hidden neurons, we can now compute the output for this one. Take this kind of weighted sum based on the inputs. And so you can imagine that you can learn more and more complex things here. And I'm not going to do all the math here, but you could see that if you plug in 1 and 0 for those outputs, you should get an output of 1, which is exactly what we expected. So you can imagine that as you start making more complicated networks, you can learn more complicated functions. That even though each neuron on its own is very, very simple, it's just this weighted sum, has its own coefficients for its inputs, and then you just give it to the activation function, that it can learn in sequence many, many complex things. So here's kind of a one-slide version of all of this math. A 2-layer neural network, one with 1 hidden layer and 1 output layer, can learn XOR. And I showed you all the coefficients for these. This is just walking through a more general version of all that math I just described. But in particular, each individual neuron here, actually I'll use different colors, use these input features, then come up with outputs. And those outputs then become inputs for the next thing. Okay. So you can learn XOR with a 2-layer neural network. So it turns out that neural networks have more flexibility in how you specify them. I described 2 layers, but the number of neurons you put in each layer and things, how you structure it with how many layers, that's all choices you have to make. And we'll talk a little bit about kind of some theory behind how to think about this. So sometimes one thing that's a bit confusing is people mix up terminology a lot. Sometimes we'll call this a 2-layer neural network because there's kind of 2 sequences of transformations for the input to the hidden layer and then the hidden layer to the output. Sometimes people also just call this a 1 hidden layer neural network because you always will have input output, and then it's just however many hidden layers you have. And this math is just showing you a general version of the specific network I showed you here. Is that, well, yes, you just take the weighted sum of the inputs and then feed that to our activation function. The activation function here I call G. This is our activation function. And that becomes the output for a single neuron. And then we can use those outputs as inputs for following neurons. And so we can just keep going through and through this way. So just like in the notation I showed you in the other slide, this value here is the output of the kth neuron. And then we use that to feed into the next neuron, weighting them, and so on. It turns out that 2-layer neural networks are sufficient to learn any function if you allow enough nodes in the hidden layer. So I'm going to switch to regression for just a second. But it turns out that you can learn any regression function with just a 2-layer neural network, or a neural network with 1 hidden layer. The trick, though, is to learn more complex functions, you'll need more nodes in that hidden layer. You'll have to have more and more nodes in that middle part. The intuition for this is that each one of these individual neurons is learning a step function, right? It's learning a weighted sum of its inputs, and it has an activation function that takes that weighted sum and turns it to an output. And in the case of our step function, or the sign activation function, it's either 0 or 1. A bunch of times it's 0, and sometimes it's 1, and there's a switch point in between. For different settings of the coefficients, you might learn a different step function. With different coefficients, where this boundary between positive and negative lies changes. So then when you take these two kind of outputs as input for your next neuron, you can now learn a weighting of these things that let you learn a more complicated function. So even though each individual neuron is only able to learn this kind of step, together, when you weight their choices separately, you're able to learn more complicated functions. And in general, with more and more neurons in your hidden layer, you could learn even very, very complex functions as just a combination of many, many, many steps. With more neurons and how you weight between them, you can learn more complicated functions. And there's a link to an article here that you could read if you're interested that walks through the proof of how any 2-layer network with as many nodes as you need can learn any function. That any function's learnable with just a 2-layer neural network. And what we'll talk about in class today, because we're basically done for right now, is more complex structures with more layers and how those can even learn different complicated functions. Even though a 2-layer neural network suffices, it's generally not powerful enough with real-world data to capture a lot of things. This is a bit more of an argument of theory, that you're theoretically able to learn any function given enough capacity in your hidden layer. So in class today, we're going to talk about kind of how to learn these weights automatically from data and some more design decisions about how you structure these networks.